Machine learning algorithms operate entirely on pure mathematics. At their very core, they are strictly designed to evaluate numbers. Take a look at this equation interface. If an algorithm attempts to multiply a weight of 5 by the word blue, the system immediately throws an error. It cannot calculate text. But real-world datasets are heavily populated with text-based categories, like names of cities, various distinct colors, or even animal species. To fix this, we use a technique called OneHotEncoding. It translates words into numbers without changing what the data actually means. Open up your Python environment and load a dataset that contains at least one text column. Translating these text columns into a math-friendly format is a required step before you can train any predictive model. Here is a standard data frame loaded into a notebook. We want to focus on this city column containing New York, Paris, and Tokyo. These specific cities are nominal categories. That means they represent distinct identities with no natural mathematical rank or order. Paris is not mathematically greater than New York. A common mistake is to assign a sequential integer to each category to solve the text problem. For example, assigning a 1 to New York, a 2 to Paris, and a 3 to Tokyo. This is known as label encoding. Watch what happens on this scale. The algorithm reads these arbitrary integers as quantifiable weight, concluding Tokyo is 3 times as important as New York. We must reject this method for nominal data. It teaches the model false relationships. Sequential numbers only work for ordinal data, where your categories actually have a true inherent rank, like small, medium, and large. Treating distinct categorical identities as ranked numerical values breaks the predictive integrity of your model before you even begin training. Instead of a sequential ranking, we need a neutral, unbiased way to represent these categories mathematically. Notice how the city column splits horizontally. We expand it into 3 new columns, a binary vector. A matching row receives a 1. Simultaneously, inactive columns receive a 0. This is mutually exclusive. Only one category is active per row. These binary 1s and 0s act strictly as true or false flags. They do not carry any mathematical weight. This specific matrix design allows the algorithm to recognize distinct categories without inferring a false hierarchy. Let's transition back to the practical Python environment to execute this on our dataset. Looking at this code block, we rely on a pandas function called getDummies. The syntax targets the original data frame, and then we specify the exact column we intend to expand. The OneHotEncoder function from Scikit-Learn is a valid alternative tool for the same job, but pandas is generally faster for immediate exploratory data analysis. Execute that code cell to trigger the transformation. Comparing side by side, the text column on the left is deleted. In its place, the function injects 3 new binary columns. Isolate this first row to verify. The 1 and 0s are correctly distributed based on the original values. Your dataset is now entirely quantitative and structurally sound for algorithm ingestion. We successfully converted raw, incompatible text into a countable, mathematically safe format. Deploying this binary vector safely bypassed the ordinal trap. However, generating these mutually exclusive columns has inadvertently introduced a severe duplication of logic. We are stating the same fact multiple times. If a row isn't New York and it isn't Paris, the math dictates it has to be Tokyo. Predictive algorithms penalize models containing multiple columns that provide the exact same mathematical information. This creates a structural error known as the dummy variable trap, which we will solve in the next step.